All right, let's get right into it. Something really historic is happening in the world of the Linux kernel. For the first time ever, this massive software project, which has been built exclusively on the C programming language for its entire life, is officially bringing in a second language, Rust. Now, this is a monumental shift, so today we're going to break down exactly why it's happening, how they're pulling it off, and what it could mean for one of the most important pieces of code on the entire planet.
I mean, think about it. For over 3 decades, C has been the one and only language of the kernel, and for good reason. It's incredibly fast, it's powerful, and it lets you get right down to the bare metal. But all that power, well, it comes with some serious risks. So now, after years of talk and a whole lot of work, a new voice is joining the choir. And that voice is Rust.
So what is this, really? Officially, it's called the Rust experiment. It all became real when support was merged into kernel version 6.1. Now let's be clear, the goal isn't to rewrite the entire kernel overnight, not even close. Instead, it's a really strategic move to see if Rust can be a safer way to write new code, especially for things like device drivers and other standalone pieces.
And that brings us right to the heart of the matter. The main reason for this massive change. It's not about adding flashy features, and it's not really about performance. It all comes down to one word: safety.
It's a perfectly fair question, right? You've got to wonder. The Linux kernel is everywhere. It runs your Android phone, it runs the world's biggest supercomputers. The old saying goes, if it ain't broke, don't fix it. But here's the thing. While the kernel isn't broken, it does suffer from certain kinds of bugs that have been a problem in C for decades.
And this is where we get to the core of C versus Rust. With C, you get incredible power, but it's also famous for being prone to really tricky memory safety and concurrency bugs. And these aren't just little glitches, they can become major security vulnerabilities. Then you have Rust, and its biggest selling point is that its compiler is designed, from the ground up, to catch these exact kinds of bugs when you compile the code, before it ever gets a chance to run. It's a total game changer. You're moving from a world where safety is 100% on the programmer, to a world where the language itself provides this incredible safety net.
And honestly, the kernel documentation itself explains the strategy perfectly with this quote. So what does that really mean in plain English? It means you don't just dump a bunch of Rust code into the mix and hope for the best. No way. The plan is to build a very carefully controlled boundary. Think of it like a safe wrapper around the existing C world. That way, any new Rust code can talk to the kernel without accidentally bringing in those old classic C bugs.
Okay, so safety is the why. That makes sense. But what about the how? How in the world do you connect 2 totally different languages right in the heart of an operating system? Well, you do it by building a very, very carefully designed bridge. The best way to picture this is a bridge with some really strict security guards. The Rust code is on one side, and the giant, complex C kernel is on the other. You can't just wander across wherever you want. Nope. You absolutely have to go through the official, well-defined, and, most importantly, safe checkpoints that have been built for this purpose. So the first layer of this bridge, the very foundation, is something called bindings. These are actually generated automatically by a tool. Think of them as a raw, direct dictionary that just lets the Rust code see the C functions and data types. But, and this is a huge but, this entire layer is explicitly marked as unsafe. It's the plumbing, you're not supposed to touch it directly. So, on top of those unsafe bindings, developers build what are called abstractions. And this is the crucial safety layer. These are beautiful, handwritten Rust APIs that wrap up those dangerous C calls and present them in a way that's totally safe and natural for a Rust programmer to use. This is where all the magic happens.
And all of this leads to the golden rule. The absolute #1 rule of writing Rust in the kernel is this. If you're writing a new driver or some other module, you are basically forbidden from touching those unsafe bindings directly. You must go through the safe abstractions. And that's not just a friendly suggestion, it's a hard architectural rule that keeps that clean line between the safe and unsafe world.
Now, you might be thinking this is all just theory, but it's already happening in the real world. We're seeing Rust being used for some really complex stuff. The Nova GPU driver, for example, is a huge project being written in Rust. We're also seeing safe Rust abstractions being built for fundamental kernel systems, like interrupt handling, IRQs, and even for the APIs for PCI devices. So yeah, the experiment is well and truly underway.
So maybe you're intrigued. Maybe you want to try this out for yourself. How do you actually get a kernel compiled with Rust support turned on? Let's quickly walk through the basics.
It really boils down to 3 main steps. First, you got to get all your tools in a row. You'll need a newish Rust compiler, that bindgen tool we talked about, and the LLVM/Clang toolchain. Second, you just have to dive into your kernel config and flip the config Rust switch to on. And finally, step 3, you build it. Just run make with the LLVM=1 command.
And here's a little pro tip for you, straight from the kernel docs, that could save you a real headache. Before you kick off that big build, just run this command: make LLVM=1 Rust available. It's a super quick check that just tells you if the build system can find everything it needs. So much better than waiting for the build to fail halfway through.
So, we've covered the why, the how, and the how-to. Let's just zoom out for a second. What does all this mean for the future of Linux? Where could this experiment go?
So, let's just recap the big takeaways. First, Rust officially landed in kernel version 6.1. Second, the #1 reason, the whole point, is safety, to prevent entire categories of bugs before they ever happen. Third, it all works because of that super strict separation between the raw, unsafe bindings and the nice, safe abstractions. And finally, remember, this is a living, breathing project that's happening right now.
And that brings us to our final thought, the really big question. The door has been opened. We're starting with drivers and new, self-contained modules, but the potential here is just enormous. As that foundation of safe Rust abstractions gets bigger and bigger, could we eventually see parts of the networking stack get a rewrite? Or file systems? Or even parts of the core process scheduler? That's the billion-dollar question, and the answer is going to be written line by line in the kernel's source code for years to come.